Sorry about the late. Okay, I can hear your voice. Okay, sorry about the late.
My tone so
This is on. This mic is on.
honest.
Okay, should move now. But this is not affecting others. I can log out and log in. Yes. Okay. Okay. Sorry, boss. Mic is
Santosh is talking that small window that
so hide the controls. Let's not play too much. Let's just start the lecture. Okay. Hello. So this will happen. Just change the camera. Yeah. Logic. Okay. So we can finally start. Sorry about So today, on the camera, let me send a video. That is still not working. Is it a video? No, connect that one. Screen share working?
Yes. Yeah.
Okay. And can I do it while we start? Yeah. So my sincere apologies to people. Okay. So we can start now. Sorry. Okay, so what we'll be discussing today are the emission from moving charges and going towards a process called synchrotron emission. Now, many of the topics that I will discuss will not be dealt with in detail because they are usually taught at a higher level, either in masters or in PhD graduate school. But what I would like you to take away is some of the basic concepts of what are the different mechanisms depending on, and some of the fundamental processes that it uses. Okay. For example, I will not write what is this. This is form of electric field. How do you get it? You find out the retarded potentials. As you find out what electric field calls due to motions of charges, and then you find this form of electric field. So this is electric field of a moving charge. It consists of two parts. First, you see there is something that is varying as 1 by r squared. Second part, that varies as 1 by r. Within brackets, I have written retarded, RET. What does it mean? Suppose the charge is moving along this line. At a certain point during its course, it emits some radiation. That's this, I call this point PR. This radiation will travel towards the observer located at a distance r from the point it has emitted the radiation. So this travel time of the radiation from the previous location of the charge towards the observer is called the retarded distance. So all the phenomena that we will compute will be computed when the charge, whatever the charge's velocity, position, momentum was at the retarded location. So by the time at time t, when we are observing this charge, the charge will travel a distance v t minus tr at this location. So this is the concept of retarded times. When we observe or we get the information about the changes in the electromagnetic fields at the point of observation to find what the fields or what the locations or the positions of the charge was at an earlier time, which we refer to as CR. Now, just going through the whole set of Maxwell's equations, basic fundamental Maxwell's equations, you can come to this formula of the electric field. You can, if you want to, go through the whole details in Jackson. And that is not the point of our lecture. So, what I would like you to focus on is how these two terms look like and the spatial variations of these two terms. So, for example, this term has r cap cross r cap minus beta. Beta is velocity by c cross beta dot. This is the time rate of change of the velocity of the acceleration term. Now, suppose the charge is not accelerating at all; it is moving in a straight line. So this term drops out. Fine. Then we are just left with this term. This term has a little complicated expressions here. We have this kappa on the denominator, and kappa looks like this: 1 minus r cap dot beta. Everything computed at the retarded position. Now suppose the beta is very small. Very small. We can neglect any relativistic effects. So drop this, drop this, drop this. And the retarded times are also not very significant at that time. In that case, this just becomes 1 by r squared, the standard Coulomb's law. So the charge motions are very slow, or the motions are almost negligible. That is the electrostatic regime. You recover the standard Coulomb's law. It's fine. Now let us look at this term here. This is dying as 1 by r. So before, okay, it's like a 1 by r. So if do you all know about the Poynting flux? You must have gone through some course in the Poynting, right? So Poynting flux is the amount of energy carried per unit area. And what is the Poynting flux looks like? it's E cross B, C by 4 pi, depending on what kind of rotations you're using. If you have CGS, you'll have C by 4 pi. The magnetic field for this charge now looks something like this, R cross E. So if we try to get the magnitude of the Poynting flux, this will be E cross B, which is R cross beta dot and whatever, this term cross this term. The effective variation of the Poynting flux will be 1 by R square. Why? Because you have the E appearing twice. So the magnitude of the Poynting flux, which is the amount of radiation, amount of energy being transmitted at a given distance per unit area, that is 1 by R square. If you go from one place to another point, and if it's sort of say spherically isotropic, how does the area increase? R square. So the area increases R square. The Poynting flux drops off as 1 by R square. So total energy transmitted is constant. So this term actually tells you that whatever energy or whatever emission is being emitted by the moving charge, that can be transmitted to infinite distances. So this is the term we call the radiation term. Similarly, look at this term. This is falling off as 1 by R square for the electric field. Go to the Poynting flux, it will be 1 by R to the power 4. Right? Because it will be E square, mod E square. Multiply by the area, you still fall off and 1 by R square. So this term will fall off very rapidly from the location of the charge. Of course, how rapidly it falls depends on this numerical coefficients. But you can see there's a charge factor here which is already quite small. So very close to the charge itself, this term drops out. But this term is not zero. It's a non-zero term. So close to the charges, close to the current carrying wires and everything. If, for example, you have all learned the bias of a simple wire carrying current, etc. If you have gone through Griffiths, there's a nice problem in Griffiths. You slowly vary the magnetic field. What is the Faraday rotation, Faraday induction, etc. You can draw the loops, find the electric field, variation of the electric field at a certain point away from the wire. Those are all fine. But if you work out to the entire details, you find that there is another term which will fall off much more rapidly. But for our purpose of understanding radiative transfer, this term can be safely ignored. So we'll focus on this term for the purpose of radiative transfer and understanding what is the emission due to charges. This is a very nice example of, okay, so this example is from repeat line. What it shows is how the nature of the field line changes as you have acceleration. So it requires you to understand what is the nature of this r cap minus beta. So if you look at this diagram, for example, this is the capital R from the previous position of the charge to the current location. And by the time the radiation travels from this point to this point, so this is TR and this is T, the charge would have moved at distance V T minus TR. Okay. Now what is R? R is nothing but the time taken by the radiation from here to here. But within that time, the charge has moved this distance. So Vt minus Tr is nothing but R times V by C, which is R beta. Now if you just look at the vector notation, so this is R beta plus the small r. Small r is the current location of the charge towards the observing point. That is capital R. This is the basic vector diagrams. So if you find out what is the distance from the current location of the charge, not the retarded point, that is R times R prime minus C, which is this. So very interestingly, if you don't have the acceleration term, forget it for now. If the charge is moving, although we are calculating everything at the retarded time, the direction of the vector always points to the current location of the charge. A nice example of this is, suppose a charge is moving along the x-axis with some uniform velocity. There is no acceleration. So you see the vectors would always point like this. It will not be radial symmetric, but the vectors would point like this. Forget the initial shell here, just look at this vector. So if the charge had just continued like this, the vectors would have pointed towards the current location of the charge. You draw these imaginary lines coming towards it. So this is how the electric field of a moving charge looks like, the outer contours. Now suppose I have done an experiment by which I have stopped the charge abruptly at x equals to 0. So from x equals to 0 onwards, the charge is not moving. So then at this location, suddenly the electric field becomes radially symmetric. Electrostatic Coulomb's law. But these points here do not know that the charge has stopped. So if the charge has stopped moving suddenly by starting from uniform velocity, there is deceleration. So this term has contributed to the electric field distribution. You can see that the contours of the electric field of the outer regions are still pointing towards the most location of the charge, as if the charge would have still traveled here. But slowly the electric field is being stretched and wrapped so that it is becoming radial. So you have a shell of radiation, a shell that is moving outwards, carrying the information that the charge has stopped. So this is how the electric field lines of a charge would change of a moving charge suddenly stopping. This diagram tells you two nice things. One is what is the electric field distribution of a moving charge, a constant velocity, no acceleration. And then if you suddenly change the charge, stop the charge, how does the electric field change and carry this information? This is how it is unwrapping itself and carrying it. Okay, so from here on, for the purpose of radiative transfer, under different kinds of physical processes, we want to calculate what is the motion of the charge. Then we have to calculate what is the acceleration vector. And using this, we have to calculate the electric field. Once we get the electric field, we get the Poynting flux. Once we get the Poynting flux, we get the intensity.
From like for a star, why do we always just have the 1 by r square term and not the second term?
Why do you have this? Why
Like
do
the
you have
flux, we always take it as it falls as 1 by d square, which is the first term, right?
in the flux? No, sorry, repeat your question. So where do we have the 1 by r
Like
square?
from a star, when you have some,
From a star, okay.
when you measure the flux, you always take it to like it falls as 1 by d square, which is the first term, right?
No, but this is electric field.
But like the energy would,
Poynting flux is square of electric field.
yeah, so this would
So
become
this will be 1 by r to the power 4.
into r square, the whole thing. So 1 by r
So
square.
1 by r square is this thing.
But for this, the energy would be constant through a shell.
Yes.
We never include this term. So,
No, energy being the constant meaning so from a single point. The intensity is from a single point. If you then go back to the previous example, so from a single point, you can find out what is the energy going towards this place. So that is constant. Intensity along a given line is constant. I did not show this, but this derivation is there in Radiative book. Wherever you take two different areas, find what is the solid angle subtended by one area to the other, this one to this one. You'll find that the specific intensity along one line is always constant. So this talks about the specific intensity of one line, but intensity about one small point doesn't make any sense because intensity is per unit area. So you have to integrate with the entire area. That falls under the aspect. Okay, so as I was saying, all we need to the sequence of logical steps we need to understand is first we need to find out the acceleration vector for the given physical process. Once you have the acceleration vector, find the electric field, find the Poynting flux, and you are done. Before we go through that, there's another derivation that is very important and for you to remember. It's called the Lamar's formula. This is done for the non-relativistic regime. I'll soon go to the relativistic regime and show you the. I'll not show the derivation of it, but it's just a Lorentz extension. So for very small velocities, theta less than 1, the radiative part what we are doing is dropping this kappa terms, expanding this kappa. Kappa is 1 minus r cap on theta. Expanding these terms. The radiative terms can be written like this: r cap plus r cap plus the acceleration term q by rc. And magnetic field is this. If you find go to the Poynting class now. I will warn you that I will put CGS notations here. The notations will slightly differ from Jackson because you will not have the C and 4 points. But for astrophysics, we mostly use CGS. That's why it's easier for us to relate the final expressions when you use limit astrophysical concepts. So you get the ERAD, the modulus of the ERAD, substitute here. This is energy per unit area. You get to the solid angle, the unit area that it's going through is r squared d omega. R squared is from the point of observation to the distance to the point where you find the unit area. This is basic definition. So if you do all that, you will find the solid angle distribution of the power being emitted, dp d omega. And this is how it looks like. So forget about the derivation. We will give you the slides, you can work it out later. But look at the variation of this object. So sine theta. So this is the acceleration vector. This is the direction towards which the radiation is going, or the observer's direction. Theta is the angle, the acceleration vector, and the observer, which also comes from r cap cross theta dot. So this looks like dp d omega, or the angular distribution of the power. Looks like this. So firstly, you can note this is not isotropic emission. This is anisotropic emission. Along theta equals to 0, along the acceleration vector, there is no emission. dp d omega is 0. dp d omega is maximum perpendicular to the acceleration vector. So this is actually called a dipole pattern of the emission field. So now you integrate over the solid angle, you get this relation. So the total power emitted by the charge is 2 times v square times the acceleration square divided by 3c cube. Again, the c will not be there if you are working with SI. This is called the Larmor's formula. Now you can quickly understand what I'm going to do if I have a relativistic system. These are constants. Now I have to find a proper relativistic Lorentz invariant form of the acceleration vector. If I can write this one in a Lorentz invariant form at the rest frame, then I'm done. So what I'm going to do is I'm going to write this in the rest frame of the charge, instantaneous rest frame, but the velocity is zero, but acceleration is constant. And then transform the acceleration vector to the lab frame.
So the power would be Lorentz.
The power is Lorentz. No, I'm finding the total power. If the power is there, this is the quantity I'm getting. After the Lorentz transformation, this is the power I'm getting in the lab frame. It's not Lorentz invariant. In intensity by nu q is Lorentz invariant. I'll not discuss this, but this is there in the textbook. So again, what is important for you to take away from this is this dipole nature of the radiation, because we'll use it soon to understand how the radiation pattern looks like for a very fast moving charge. And the fact that total power is given by this. So the thing is, if I have an electron, say, moving in a circle, if it's moving in a circle, of course there is an acceleration in it. Right? So you have studied about gyration of electrons around the medium. So if it's gyrating, there's a centrifugal force, whichever way you want to call it. So there is acceleration. If there is acceleration, there is radiation. The total power emitted for this, if the acceleration vector is constant, which is the case if it's a uniform gyration, you can quickly find the total power being emitted. This is the total power. If you now put, suppose this is a problem usually given assignments. So this is the electron moving around. Now I want to find what is the power at this angle. Then you have to compute this distribution. But the total power can be quickly found by this. Why I'm saying so much about this? Because I'll quickly use this soon, 2 slides from now. Before that, some basic recap of Lorentz transformations. Length, time, I'm not going through. What I really wanted to remind you is how the velocity is transformed. And the velocity transformation gives us the angle transformations. So these are the standard Lorentz transformations you can look at the textbooks. So a theta in the k prime plane, k prime is the moving frame, for example. So theta prime in the moving frame would be different from the theta we observe in the static frame, lab frame. And this is how the angle transforms. So this is the reverse transformation, theta with theta prime. And for very fast moving objects, we can make some approximations. The theta goes as 1 by gamma. So sine theta 1 by gamma, theta gamma is very large, gamma say Lorentz factors of 100 or 1000. Then we can approximate this as theta equals 1 by gamma. Now what happens, what is the significance of this? Significance is, so you maybe have encountered this concept of relativistic beaming, where a charged particle moving in a particular direction, all the radiation will be concentrated along the direction of the charged particle. So mathematically, what does that mean? Now suppose in the instantaneous rest frame of the charged particle, the emission is isotropic. Okay? So this is just a pi by 2 angles in the rest frame of the charged particle. And all the emission is isotropic. You transform to the static frame or the lab frame. These blue lines, which was pi by 2 in the rest frame of the charged particle, become like this because of this angle transformations. They become a cone, but the half angle of the cone is 1 by gamma. It does not mean that there is no radiation here. If you now this is pi by 2, had I taken 120 degrees, it would be still small line above this. So what does this mean? It means that half of the radiation emitted in the charge's rest frame is concentrated in a small cone of angle 1 by gamma. And the radiation pattern is consistently towards the forward direction. But you will find out if you put in the formula here that there is finite radiation in the opposite direction. So theta is, if you put theta equals to pi, just work out this, you will find that there is a line extending here. Theta pi remains unchanged. What does that mean? Does that mean that there is a reverse radiation going on? It is just one angle. Radiation from one single angle now will not give you significant output in terms of power. So the major amount of radiation will be in the forward direction. So whenever people will tell you that the radiation is with an angle of 1 by gamma, what they actually mean is half of the radiation is with an angle of 1 by gamma. The rest of the radiation you can find relative more. You can say this is half. So if you go say 60% of the radiation, you take appropriate angles here and see what is the angle corresponding to this. Something very small extension of 1 by gamma. So we usually consider this radiation to be within a cone of 1 by gamma. So this is called relativistic beaming of moving charges. And the charge moves at a very high Lorentz factors, and the Lorentz factors I'm talking about are 100 or more. It can extend up to 10 power 6, a million. Lorentz factors of a million. That is very high. Such highly energetic electrons can be generated by acceleration shocks or by other mechanisms. So shock acceleration is just one of them. So you start off from a normal thermal distribution of electrons from a thermal gas. The gas passes through a shock or a connection, two magnetic fields oppositely directed. As the magnetic field come close together, they get destroyed because they're opposite magnetic fields. As they get destroyed, you can't have destruction of energy, so that gets transformed into thermal energy. So that is the basics of magnetic reconnection. In this process, particles crossing the magnetic field line onto this thermal region get accelerated. So there are different kinds of acceleration mechanisms, but these transform the particles from a normal thermal distribution to a very high Lorentz factor distribution. Okay, now I talked about the dipole pattern. So forget all this mathematical muck here. Let's just look at the diagrams. So the dipole pattern was this in the charges rest frame. You go to the static frame, the two lobes will be bent in the forward direction with an angle from the charges direction to the midpoint of the lobe being 1 by gamma. So this is when the charge is moving along the direction of the acceleration vector. what happens if the charge is moving perpendicular to the acceleration vector? So acceleration vector is here, the charge is moving in this direction. What happens here? So this is actually the case when you have a gyrating electron. The instantaneous velocity vector is perpendicular to the acceleration vector. So you'll have this case actually. So this lobe becomes extended, but this lobe falls onto the first lobe. So the back lobe gets quenched onto the forward lobe. And again, the tangent of this lobe is 1 by gamma. I mean, you can work out all the details. I'm not going into all these things, but essentially you can find out the relativistic transformations of angles and the power, etc. But physically, this is what it looks like. So even in our case now, next slide is going to simplify now. It doesn't magnetic fields. So I'm slowly gravitating towards a case where charges are gyrating along a magnetic field. These charges are relativistic, and if these charges are moved, what is the effective emission that I'll get from this charge? Okay. So this phenomena is called synchrotron radiation. So radiation from relativistic or non-thermal electrons gyrating along magnetic fields. And these electrons are highly relativistic. If the electrons are not relativistic, they can still be non-thermal, but not highly relativistic, then we'll get something called cyclotron radiation. Okay. So this is the relativistic equation of motion of charges. The gamma is taken, so initially you should have m times d gamma dt, by c t equals b. The gamma is taken out because there is, I'm ignoring radiation for now, but the charge, the energy of the charge does not change by gyrating along the magnetic field. So if you work out the standard expressions, you will have a Larmor frequency, the frequency of gyration. In the non-relativistic case, if you had worked out through Griffiths or other books, you would have QB by n. The C would not be there in SI units. For the relativistic case, you have an addition of gamma. So QB by gamma MC. So just to note, the definition of Larmor frequency all through now will have a gamma inside it. This tracking the gamma is important. We'll see soon why. And then there is a Larmor radius. This is the perpendicular velocity defined by. The total power emitted, now I'm using the Larmor formula. Okay. So this is the relativistic form of the acceleration vector. It looks like gamma square, so acceleration vector square is gamma to the power 4 perpendicular component square plus gamma square by component square. This is how it looks like. You can again look at standard textbooks for derivation. But for our purpose, we have the A parallel component 0 because the charge is gyrating around the the acceleration will be perpendicular to the charge. It's only this term contributes. If you work out some of the details and use some basic scaling laws, like this is called the classical electron radius E squared by mc squared, you can write the expression of the power being emitted in a very nice compact form. Now let us spend a few brief moments to understand what are the dependencies of this power formula. The power emitted by a relativistic electron gyrating along a magnetic field depends on square of the Lorentz factor. It also depends on square of the magnetic field. So higher the energy of the electron, the more the amount of radiation it gives. The stronger the magnetic field around which the electron is moving, more the radiation it gives. The rest of the things are almost constant. So beta perpendicular is there. It actually gives you some non-trivial contribution because if it is beta perpendicular, it gives you a sine alpha beta. Otherwise, beta can be dropped because it's almost equals to C because the charge motions are very fast. And the other terms are constant. So if you average over all angles, so this is sine alpha along one direction. If you average over all angles, it's a average over the sine square alpha. Simple expression, you will find that this looks like this. This can be expressed in a more convenient form because V squared by 8 pi is equivalent to the energy density of the magnetic field. If you are not used to this concept, you can look up how the energy conservation looks like as you work out the Poynting flux. Or if you go through the fluid course, I'm sure Nishant will tell you why this is true. So if this is the form, then we can again write this in a bit more convenient form as 4/3 sigma t. Sigma t is 8 pi r naught squared by 3. It is the Thomson scattering cross section. I will come to Thomson scattering later on when we discuss scattering. Beta square, gamma square, energy density. Why is this important? Because you will soon see when I discuss Compton scattering in the next lecture. Instead of UV, you will have the energy density of the radiation field. So the expression of synchrotron radiation and Compton scattering have the same power dependence. So P is same, 4/3 sigma T beta square gamma square is just U radiation. So look at it from the point of view of electrons now. Electrons can lose energy due to synchrotron. Electrons can also lose energy by interacting photons surrounding it. So that is called Compton interaction. So a standard source of photon for electrons would be cosmic microwave background, CMB, which you heard of in a seminar last week. So if you have CMB and magnetic fields both present, the total loss of the electrons would be whatever constants is here in front times UV times URAD plus URAD. So in a region where the magnetic field is low, the radiation density is higher, the primary energy loss of the electrons would be via Compton scattering. So when we have to model the electron spectrum, we take into account both of them. But I will not discuss Compton today, focusing mostly on electrons. So now we are slowly trying to get towards a more mathematical derivation of synchrotron, which I will not discuss. But I wanted to give you the salient features of the synchrotron radiation. Okay, the mathematical derivation is more complex. So first thing you need to understand is the fact that the radiation is beamed. So if this is the trajectory of the electron and this is the observer will see the electron only at a small finite time along its path because all of the radiation is within this cone of 1 by gamma. Not all, but most of the radiation. So unless the cone comes within the line of sight of the observer does not know that the electron is moving around. So during the entire trajectory, only certain parts of the trajectory between 1 and 2, which corresponds to the tangent of the cone, it's an approximation, of course. Observer will also see slightly away from it because you can see some radiation, but I'll approximate that all the radiation is within an angle of 1 by gamma. So this is a tangent that is entering the observer's line of sight. This is a tangent that is exiting the observer's line of sight. So that is why within point 1 and 2, the observer sees the radiation. If you work out some details, you will find that this time gap can be expressed as gamma cube theta b sine alpha. I'm not showing the derivation of this. And this gamma cube, actually omega b has a gamma in the denominator, right? So this is essentially gamma squared sine alpha to the power minus 1. So if the gamma is high, always sees a small pulse of radiation. So as the charge is gyrating, you'll see blips, like you see the ECGs, small blips, as a repeating function of time. So what you are seeing is a pulse of radiation. Now, if you are seeing a pulse of radiation, the time is something small pulse of radiation. But if it's pulses, then the best way to understand what is the spectral distribution of this pulse radiation is go to the Fourier domain. Now, intuitively, you can think, because there was a question also in the last lecture, why do we want to go to the Fourier domain? Now, suppose if you have a perfect sine wave stretching to infinite time, then in the Fourier domain is just one peak. So the spectrum would be just 1 point in the entire spectral distribution. Now, if you don't have a perfect sine wave, so sine wave is there for only a short period of time, then if you do the Fourier transform, this is a sine wave multiplied by a box function. If you have done Fourier transform, you will find the box function will give you wiggles like shape like this, and then wiggles. So then the spectrum would look like this. Now, if you have a pulse radiation, then the spectral distribution is best done then again in the Fourier transform. And this is why we need to go to the Fourier transform. So this is a more mathematical way of deriving it. I'll just sketch the brief points. This is just to convince you that Fourier transforms give you the spectrum. So the total Poynting flux is energy per unit time per unit area is C by 4 pi E square, mod E square. E is a function of T. Now what I'll do is, I'll do the total energy integrated over the entire time. So if it's a small pulse, we can extend the time integral to infinity because we are not seeing more than a pulse. It's almost like a Dirac delta function with a small interval of time. So integrate over the whole time. So the total energy that you see is d omega by dA per unit area is this. Now this is the Parseval's identity for Fourier transforms. You take the time integral, convert into spectral domain. This is what you get. If you are not familiar with this, I suggest you look up any standard books on Fourier transforms. And also, if since this is the integral here is symmetric about the omega 0, then you can transform it to from 0 to omega and multiply by factor. So this entire integral here, you can transform in terms of e omega square 0 to infinity. So this is the integral in the spectral domain, frequency space. Right? If I want to find the spectrum, it means energy per unit frequency. I take a derivative of this, or just take one small integral over a small region. So dw by dA d omega is c by c times e omega whole square. Now, if this pulse emission that we are seeing is only for a finite duration of time, then what is the total emission per unit frequency per unit time? I just divide by the time period of the pulse. So c by t, which is the time period of the pulse, times the Fourier spectrum gives you the spectral distribution of the energy or the spectrum.
But would you keep seeing the pulse?
Yeah, this is for one pulse. For each pulse, we see one pulse, we can do this mathematical argument for this one pulse. If we keep seeing the pulse, then we have to keep on doing it. But keep on adding.
So we have to take the Fourier transform of like a multiple pulse.
And they can be added. It's additive. Okay. You can just divide this into two parts and then just keep on adding. What is important to know? So this is the box function. So finite sine wave, it is peak at the frequency of the sine wave with some wiggles here. What is important to note is if the pulse is very narrow, the Fourier transform is wide. For example, if you take a Gaussian in the real space and go to the Fourier transform space, it will also be a Gaussian with the width being inverse of the width in the real space. So in this case, if my pulses are very narrow, you can understand there will be a wide distribution in the frequency space. So the emission that I will get from this electrons moving around the magnetic field will be distributed over a wide range of frequencies. So I will not go through all of this. So this is how you do the full detailed synchrotron. I don't want to scare you, but I just wanted to sketch the basic points of how you approach this problem. So what you have to find out is find some vectors along the direction of the observer. Find two other vectors, keep epsilon perpendicular parallel, give you the two polarization. Then find the instantaneous acceleration vector. Decompose the acceleration vectors along this Cartesian domain that you have to construct. Find out the full n plus beta. So whatever the terms were there in the retarded expressions that I had shown, and calculate all these details in full glory. After doing all that, you will find that the total power can be expressed in some form. I'll just skip that and show you this form. The total energy can be expressed in this form. But these two fx and gx are integrals that have been tabulated or can be computed numerically. These are like the Bessel functions, the modified Bessel functions. Okay, and the perpendicular and the parallel component, which gives you the two components of the polarization, looks like this. The total power of the synchrotron looks like this. where x is the frequency divided by the critical frequency. Now, you must have seen that I was writing this term here, which is related to the pulse width time. The pulse width time is gamma cube omega b sine alpha. I added a 3 by 2 here because as you see that when I write the full expressions, this x is related to the omega c. So the 3 by 2 was pre-attempting what I would get when I write the full expressions here. So this is how you deal with synchrotron radiation. Okay. So this is how the spectrum of the synchrotron radiation looks like. So the peak of this fx function is, so if you sum both the perpendicular and parallel component, you just have one of these unknown terms, fx, and rest of are constants or known quantities. This fx integral, again, to remind you, looks like this. So if you compute the fx integral numerically, there are expansions available, then it looks something like this. So firstly note that this is a broad spectrum. The energy is not peaked at a certain frequency. So just because electron was gyrating with a lambda frequency doesn't mean that the energy could also be peaking at that frequency. If the electron was non-relativistic, then you would have energy at the lambda frequency and its harmonics. Okay. So this is the case, and the peak of this distribution is almost 0.3 times the critical frequency. So x-axis is x, which is omega by omega c. So if I can find out the critical frequency of the electron, I can find what is the peak of the synchrotron expression, and relatively understand where the synchrotron emission would mostly be found in what frequency. So again, if I show you the expression of the critical frequency, the critical frequency depends on the square of the gamma, because omega b already has a gamma inside it, qb by gamma mc. It depends on the magnetic field and depends on the angle, sine alpha. So if I have an electron with higher energy, the emission shift towards higher frequencies. If I have an electron gyrating around higher magnetic field strengths, the spectrum shifts toward higher frequency. So this is a very nice way of understanding. If you find your synchrotron spectral distribution, you can see where it peaks. You can then gain some insight about what is the nature of the emitting region. Now, usually, what we find is the synchrotron is not given by a single electron with single energy. There's a distribution of electrons. And as I said, the distribution is in most cases non-thermal, which means it's not a Maxwellian distribution. Most of the cases, the electron energy distribution goes something like this. It's the power law. E to the power minus p e. Or you can transform it into gamma space, n gamma d gamma c gamma to the power minus p d gamma. So total power again, you integrate over the distribution function. Right? You take the synchrotron emissions from a single electron, a monoenergetic electron, and integrate over the distribution, energy distribution function of the electrons. Now you can play some tricks here. Which is this p omega will have omega by omega c. Omega c has gamma square. Gamma square is related to the energy of the electron, gamma mc square. We can now make some transformation of variables. This gamma to the power minus p you can again write in terms of the critical frequency. We'll have some constants coming outside, which we'll ignore for now. You'll find you can transform this integral into a standard integral, which again can be tabulated. And then this term outside. So the frequency dependence of a region with a power law distribution of electrons omega to the power minus p minus 1 by 2. So if in practice what we do, this is what we do when we observe, say, with something like the NCR radio telescope, EMI telescope. We observe synchrotron radiation from distant galaxies. We find out the spectral energy distribution of the intensity. We measure the intensity at two frequencies. We usually find that is a power law, not just two frequencies, but many frequencies, and find that to be a power law. If the observed radiation is a power law, then we can find the index of the power law. If we find the index of the power law, we can find what is the nature of the distribution of the electrons that is giving out the energy. So from this P here, we can find, from this index here, we can find P using P minus 1 by. So this is standard expression, very useful in radio astronomy. And this is more detailed about synchrotron, we don't require for conceptual understanding. And this is how a synchrotron map looks like. So these are jets launched via supermassive black hole. The center is the galaxy is here, small dot. You can see these two. This is a more prominent jet, less prominent jet, but big blobs of hot emitting gas. What's happening here is this black hole is launching these jets. This is slightly towards the observer, away from the observer. So this is Doppler boosted, so Doppler de-boosted. If you work out the relativistic boosting of the intensities, you'll find that it depends on 1 minus beta to the power gamma, to some power of 3. So this becomes boosted and this becomes de-boosted. So things coming towards you gains a lot of increase in the emission. Things going away from you. These jets are going and hitting the gas surrounding the galaxy, and then they're stopping here. So that is why you see these two hotspots. And then the gas is flowing back down. This is called the backflow. So along this path, the electrons are encountering shocks inside the axis of the jet itself, which is accelerating them, and that is how you are seeing the synchrotron radiation. The brightest synchrotron radiation is at this point where it just stops. There's a lot of energy from the jet being dumped onto the matter, and all this energy is accelerating all the electrons to very high non-thermal energies. You're getting synchrotron emission. So this is again the emission at different frequencies. I think this is like 1.4 gigahertz, or this is high gigahertz. This is 150 megahertz. You can see that the emission pattern looks very different. That is why we observe these objects in multiple frequencies. And another reason why you can see that this looks more extended than this. One of the reasons why this is the case is the electrons at higher energies lose energy faster. The power is proportional to gamma squared. Also, the critical frequency is proportional to gamma squared. So if you are at a particular frequency, you are preferably seeing electrons of a given energy. If you go to lower and lower energies, the loss rate of the electron energy is lower. That is why at lower frequencies, at higher frequencies, for example, let's start with higher frequency, all the electrons here have already lost their energy. So this is not empty space. It is filled. So you can see the spectral index map here. There is some non-thermal emission here. It is filled with gas, but we're not seeing that because their energy has decayed substantially beyond the detection during the hot telescope. Here you can still see, this plume-like structure which is not seen at 5 gigahertz. At 150 megahertz, this is from a GOFAR, one of the largest telescopes, radio telescopes now in Europe. You can see this structure here. Why? Because these are less energetic electrons, they are cooling down slowly, and they're still giving out synchrotron radiation. So if the electrons cool down, then you cannot see any energy, any radiation from them because their energy will decrease and then become non-relativistic. So this is the spectral index map and this is the spectrum, etc., etc. So this was what I was saying. So ignore this part now, the curve part. This is almost like a power law. If you find the index of this power law, you can find the index or the nature of the electron distribution. Okay, so I'll end here. Sorry for the delay in starting. Next lecture, we'll go for French tolerance.